Hello everyone. I hope that all of you are fine and enjoying good health. Welcome to another lecture of robotics and automation. In this lecture we shall talk about grid-based path planning, and then we shall study the trajectory generation. After that, our whole lecture will be about robot programming and different methods for programming the robotic manipulators. If you remember from the previous lecture, we talked about how we can convert a workspace into a C space or a configuration space, and that was pretty useful in case of robotic manipulators, because the workspace and the configuration space, they are not necessarily the same things, and they look quite different. So that was about motion planning. So today we shall assume that we already have a C space or a configuration space, and now we want to plan a path from one position to another position, avoiding the obstacles. So we shall see a very common method used, which is a grid-based path planning. And so let's see how it works. So let's say we have a configuration space here, and this whole area is this bounding box here. This is the boundaries of your configuration space, and so what we need to do, what we want is that we want a shortest path between let's say this is your goal location, and this is your start location, and here we have obstacles. Let's say this is obstacle, and here we have let's say this is again an obstacle, and yeah, so let's say these two we have obstacles, and what we want a shortest path from your start configuration to your goal configuration. So let's make a start location a little bit different, because then it will be much easier. So let's say this is the start location, this is a start cell, and this is your goal location. Of course, these are some values of your angles of your robotic arm, for example θ1, θ2, or in case of your mobile robot it will be some x, y locations in your configuration space. So what we want a shortest path from the start location to the goal location, and avoiding these obstacles in the path. There are several techniques that we can use, as we have studied in the previous lecture. For motion planning, there are grid-based methods, then we have sampling-based methods, artificial potential fields. Yeah, so what we are interested in, today we discuss about the grid-based methods. So in grid-based method, what we do, we put a grid containing different cells into we divide the configuration space into different cells using a grid. Okay, so these are horizontal and vertical lines, and so by this method we divide our configuration space into small cells. As you can see, these small boxes that occupy, and so we have some free cells, and this we call C free, this free cell region, and then we have cells with obstacles, and we can call them obstacle space or occupied cells. So yeah, so for grid-based path planning we have a planner, and it's called wavefront algorithm or wavefront planner. So this method, what it does, it finds a path from start location to the goal location without avoiding the obstacles. So this is how it works. So the first thing you need to do, you need to place a grid of a reasonable resolution over the C space. So resolution is also important, because if your resolution is not enough, if the boxes are too big, then it will be difficult to plan a path. Okay, the path will be not much, it will be jerky, and also it will be not be shortest path. Okay, and if the size of this cell, this square, is too small, so it means you have divided your configuration space into very small cells, then it will be computationally expensive. The algorithm will it needs more time to compute the path, and also it requires more memory. So yeah, so we need a reasonable cell size and the resolution of your grid. The next step is assign value 0 for the cells that belong to C free. So here now what we have to do, we have to assign the value 0 to the cells that are free without obstacles. So these all cells, they don't have any obstacles. Okay, so now we have assigned 0 value to the free. Assign value 1 to the cells that belong to obstacle space. So the cells that have obstacle in it, we have to assign the value 1 here. So let's assign here the value 1. We call it 1 here, 1 here. Okay, so we have only 2 cells with obstacles, so we have assigned them the value 1. The next step is assign value 2 for the goal cell. So here we have a goal cell, and because if you write here goal, you understand that this is a goal cell, this is a goal location or a position, but computer will not understand. Computer works with binary informations or some coded information in a binary sequence. So to make this goal understandable by your algorithm and by computer for further calculations, we need to assign it some digital value or digit value. So we can put here the value equal to, let's say, 2. So this is your goal. So 2 is goal, and 1 is obstacle, and 0 is the space where your robot can move, okay, without colliding the obstacles. Okay, so yeah, the next step is then explore the neighborhood for the goal cell and assign them 1 incremental value. So what we need to do, we need to look for the neighborhood of your goal. So how many neighbors it has right now? It has here, for example, if you see, it has this neighbor here, this neighbor here, it has this neighbor here. So we are taking only the neighbors that are connected in horizontal or vertical manner. We're not taking the neighbors that are connected in or you can say the neighbors that are not strictly horizontal or vertical. We are not considering the diagonal neighbors. Okay, we should take it to make the things more accurate, but for simplicity and to make things easier, we just avoid taking these diagonal neighbors. Okay, so we are not considering them. So the immediate neighbors for this your goal node, these are 3 nodes. Okay, and what we need to do, we have to assign them the value. We have to add 1 to the original value and assign this value. So 2 plus 1 is equal to 3. So we have to write 3 here to all of these neighbors. So we have written 3, 3 and 3. Okay, so that's the next step we have to do. After that, explore each cell of the neighborhood and assign the newly explored cells incremental value. So now we have to again explore each cell of your neighborhood. Okay, we have already explored. Now we are, for example, if we are here, from here we explore the neighborhood that is unexplored, and which is this one, and this neighborhood should be given the value 4. Okay, so if you come from here, or if you also see from here, this cell will have the value equal to 4, and similarly this neighbor also, 3 plus 1 is equal to 4, and if you come from here also, 3 plus 1 is equal to 4. So we have to assign here also a value of 4. This one has another neighbor which is here on the left side, and this one also we have to assign the value equal to 4. 3 plus 1 is equal to 4. So as you have seen that we have explored the neighbors of the neighborhood cells, and we have assigned values. So we have checked this one neighbor is here, which will be 4, this one 4, this one 3 plus 1 4, 3 plus 1 4, 3 plus 1 4 here. Okay, now the next step is keep repeating this process till start cell is reached. So we have to repeat this process of exploring the neighbors and assigning them an incremental value. So the neighbors of 2 were 3 3 3, and neighbors of 3 were 4 3 4 3 4, and now our wave front is located in these cells 4 4 4. Okay, so this is, you see that it's like a wave exploding. This wave started from here, the wave projected here, this was a wave front, and now the wave front of this wave is at these cells 4 4 and 4. So now we have to explore again the neighborhoods of our wavefront cells, and if you start from here, this has a neighbor, unexplored neighbor, which is here, and this has been already explored. In the diagonal we are not taking the diagonal values, and also this is obstacle, so if we explore this one and this is neighbor, so we assign it a value 5, 4 plus 1. So why we are adding 1 every time? Because we assume that moving from one cell to another cell, it cost, the distance between these two cells is 1, let's say 1 meter, or it cost to move from this cell to this cell 1 unit. Okay, either this is energy, time, fuel, whatever it is. Okay, exploring the further cells of our wavefront, if we look at here, this has neighborhood, this one also, if we come from here, this one is neighborhood, so this one will get also value equal to 5. So now our wavefront is at 5 and 5. We repeat this process, and if you see that 5 has a neighborhood, this one, which will be 5 plus 1 is equal to 6, and on this side, on the left side, it has a neighborhood, but this is already occupied space, so we cannot do anything, we cannot move in this direction because here we have obstacle. Okay, on the other side we have 5, this value here, and we have to add 1, and then it will become 6. Okay, so now our frontier is at 6, and again we explore the neighborhood, and we see that if we explore, this one has a neighborhood here which is empty, free space, and if we add here, this will be 7, and from here if we come from, then this will be also be 7. Okay, so exploring again the the neighbors of our frontier cells. In this case we have 7 and 7. So what we can do here, coming from here, 7 plus 1 8 and 7 plus 1 8, so this one have the value 8. So our starting position, or the starting cell, it will have the value 8, and the goal one we have already assigned the value 2 here. And so now what you have to do, you have to just follow the from your start node, or from the maximum value of the cell, you have to follow the lower values. Okay, so from here, if I start from here, in this case, this is a special case in which both sides have same values. But let's say if the starting was somewhere here, then this will have value 8, and here we have value 6, so it will be different. But now it has both sides same values, so you can choose any one. Let's say I choose this one here. So from 8 to 7, okay, 7 to the lower value, which is 6, and from 6 to the lower value 5, and from 5 to the lower value, which is 4. And in this case, here we have 4, and here we have also 4. So if we have same value, you can choose any one of them. Okay, it depends upon you. So let's say I choose this one here, 4, and then from 4 to 3. In this case, 4 also have 2 options, 3 and 3. So from 4, you can choose anyone. I choose this one here, from 4 to 3, and then from 3 to the lower value, which is 2, and that's how you reach the goal. So in this case, if your robot wants to move from this location to this location without colliding the obstacles, so this is the path it has to follow. Okay, there can be alternate paths also. For example, if you choose this 4 instead of this 4, then your path will be like this here. Alternatively, your path can also be, if you choose this 3 instead of this, your path will look like here. And in the beginning, if you start from here, this could also be your shortest path here, alternatively. But again, because this whole grid is symmetric, that's why there are multiple paths. So this is one of the methods how you can find the path from your start to goal location using wavefront algorithm. So yeah, so if this is clear, then we shall not go in the detail of the other methods. If you are interested, you can read it by yourself, or you can also watch my videos on the channel, and there I have also explained them in detail. But the main idea was to give you the introduction of how path planning works, and how we can find the path avoiding the obstacles, and how robot in the real world, how they do path planning, how they decide where to move, and how to not collide with real world objects and reach your destination. So this is the best example. For example, if a robot has to imagine this is a 2D world, and here we have the robot arm is located here, and actually no, it's not, it's a configuration space. But so you cannot really tell the location of your robot using the configuration space. So because this will be most probably, it's representing the position of your joint angles, θ1 in the horizontal axis and θ2 in the vertical axis. And because we got this configuration space from the a workspace that may look totally different. Okay, so if this is clear, then Now we move to a different kind of topic, and this is about trajectory generation. We talked about in the previous lecture and also in the path planning, motion planning, we talked about finding a collision-free path from start location to the goal location. But once we have the path, like in the previous slide, we found the path in the configuration space. So now the task is to follow this path actually by the robot. Okay, now the task is to also the robot has to decide, okay, with what how much time I have to take to complete this journey within this path. So all this stuff is about trajectory generation. Okay, let's see what is trajectory generation. During robot motion, the robot controller is provided with a steady stream of goal positions and velocities to track. This specification of the robot position as a function of time is called trajectory. Okay, so when you are following, when the robot is following a path, okay, so it needs to also be aware with what velocity it needs to follow this path or track. So you can say that trajectory generation is about following a path but there is also time involved in it. Okay, so you also need to now specify how much time it will require to complete this journey, or with what velocity you have to travel on this path. So this is about trajectory generation. Okay, the next subtopic we have is a point-to-point trajectories. The simple type of motion is from rest at one configuration to rest at another. So that's why it's called point-to-point trajectory. So you move like this. This is, let's say, configuration 1, and you move from this configuration to your next configuration, which is configuration 2. Okay, and then you move to configuration 3. So this is the simplest method of the path following, or so you move in a step-by-step way. Okay, this is the simplest one. We call this point-to-point motion. The simplest type of path for point-to-point motion is a straight line. So when you're moving point to point, from one point to second point to third point, and the simplest type of motion between any 2 points is a straight line. Okay, so that's why we are going to now also see what are the straight line paths and how we can make them. So for now you just need to understand that once you have a path from here, once you got some kind of path from your start to goal, so now this was a path. As we discussed in the previous slide, we did it using the wavefront planner, and it gave us some kind of path in your configuration space. And now what was in the trajectory generation, we talk about how much, with what velocity, and in how much time we have to cover this path. Okay, so this is about trajectory generation. And then we said that the simplest type of motion we can do is, or we can follow the path, is using points. So we can divide this our path into some intermediate points, and then we just connect them with straight line to just move from one point to another point. So yeah, so let's now see what are the straight line paths. A straight line path from a start to an end configuration could be defined in a joint space or in a task space. Straight lines in joint space generally do not yield straight line motion of the end effector in task space. So when we say joint space, it is actually a configuration space. And so what it says here, that straight lines in joints in the configuration space generally do not yield straight line motion of the end effector in the task space. That's because the configuration space or the joint space, this is not same as your workspace or task space. Okay, they're different. That's why if you have a straight line in your configuration space or joint space, it doesn't mean that it will also become a straight line in your task space or workspace. Okay, because configuration space or joint space, it's about angles. Okay, and the task space or the workspace is actually the real world scenario. So that's why these are different. They will never match. If task space straight line motions are desired, the start and the end configurations can be specified by xstart and xend in the task space. Okay, so here let's say we have this is a task space of a 2-hour robotic arm. So what we need here, let's say this was the x start, we call it xs, and then this is your end position, and you need a straight line from here to you need a straight line to x end, and so you want your robot to be here. So this is your task space, or you can say workspace, and here you have to define your start and end positions, and then this will be when you convert this your task space into workspace, into configuration space, then it will not always look a straight line in your configuration space. It may have a different kind of curve. Okay, so and there in your configuration space, there you can do the motion planning, path planning, and then when eventually when you follow this trajectory in your configuration space, it will eventually translate into a linear straight line path into your task space or workspace. Okay, so this was about straight line paths, and now comes the topic about time scaling a straight line path. So till now we know that what are the straight line paths, and we also know that what are point to point trajectories, and now it's about time scaling. It's more about trajectory generation. Time scaling a straight line path. A time scaling ST of a path should ensure that the motion is appropriately smooth and that any constraints on the robot velocity and acceleration are satisfied. So the main objective of task scaling is that your motion should be smooth. So this is important thing here. Smoothness we consider because in the robot motion, if the motion is jerky, okay, then you cannot really achieve most of the tasks that require some accurate motions. For example, painting, drilling, if it's your robot is shaking, jerking, and the motion is not smooth, then these operations cannot be achieved successfully. And also it may also damage the gears or the motors of your joints. So that's why we always look for smooth motion of the end effector or the robotic arm. And also the constraints on velocity and acceleration, they must also be satisfied, because if you don't satisfy the velocity constraint or the acceleration constraints, then it will also, the motion will not be smooth, it will not be not according to our expectations. Okay, so how we do the time scaling of a straight line path? What we have, we shall study two methods. One is the trapezoidal motion profiles, and the second one is S-curve time scaling. So these are two methods for time scaling. Two methods for time scaling. So this is the first one here, and this is the second one, S-curve time scaling. So the first method for time scaling, it's called trapezoidal motion profile. So trapezoidal time scaling are quite common in motor control. Particularly for motion of a single joint, and they get their name from their velocity profiles. So if you plot a velocity versus time, you get this here, you get this curve, you get this plot, and this is a trapezoid. So that's why this method is named as trapezoidal motion profile. So they are common application for time scaling of motor control, trajectory generation, and especially for single joint. So how it works is that, for example, let's say you have a path, okay, and in this path, or you can say a motion plan, and there are 3 points, 3 different configurations, and your robot must reach point 3. This is our goal location, and C1 is the initial configuration. So your robotic arm must follow this path and reach the C3 configuration, while it should also include C2 configuration. So this will be the whole motion. It will start from C1 configuration, and then it should move to C2, and then it should move to C3. Okay, so this is clearly point-to-point motion, and the between points it's a straight line motion, as we have discussed here, straight line path and point-to-point trajectory. So now we want to time scale it. Okay, we don't want that our robot should start from here with a constant velocity and move with a constant velocity and suddenly stops there. Okay, this will cause a lot of jerky motion. Okay, suddenly started from here, motor is on and your robot arm is moving, and then suddenly stops, and it will cause a jerk. Let's say if your robotic arm is holding a very sensitive equipment, or some kind of very precise tool, then it will damage it. It may get broken. Okay, so that's why we need time scaling velocity. Yes, right. So that's why we need time scaling, so that our motion is smooth while going from this configuration to this configuration. So that for this purpose we use this trapezoidal motion profile, and let's see how it works and what we want here. We want that our robot should move slowly. Initially it should move without, not slowly, it should move without jerk, and it should then move toward the target, and then slowly it should stop without jerk. So that's how we achieve that. At the beginning, what we do, we the point-to-point motion during this trapezoidal motion profile, it consists of, number one is the constant acceleration phase. So in this phase we have a constant acceleration equal to a, and when acceleration is constant, the velocity increases. Okay, you see the velocity slowly increases, and then at time ta the velocity reaches maximum value. So notice that the velocity slowly increases here. Okay, but if we don't follow these kind of clever techniques for time scaling, then when the motor will start, the velocity will already be it will increase like very quickly, like it will be like this curve. Okay, and that is not desirable. If you're holding, for example, a glass with water with your robotic arm, and the robot suddenly moves quickly with a high velocity, it may spill out the water. Especially if it's holding a paint drum or something, then it will spill out the paint. So what we do, we use this constant acceleration phase where the velocity gradually increases, and then after that we use the constant velocity phase. In constant velocity phase, our acceleration it becomes 0, and the acceleration becomes 0, so the velocity is constant. Okay, acceleration is 0 and v is equal to constant. So this is the maximum velocity the robot arm can move. So from ta to capital T minus ta, your robot will move with the constant velocity. Okay, so initially the velocity will gradually increase and then become maximum, and then the robot will move with the constant velocity. Okay, and in the third phase there is a constant deceleration phase. So in that constant deceleration phase, again the acceleration is constant, but this time it's negative. Okay, because the slope is negative, and actually the velocity it will decrease the velocity gradually. Okay, until the velocity becomes 0 at time t. So this phase your robot will be slowly gradually stopping till it reaches your intermediate point, and then finally it will stop there. So the resulting velocity profile is a trapezoid, and the S profile is the concatenation of a parabola, linear segment, and parabola as a function of time. So if you draw the function the length curve, then it will look like something like a combination of parabola, linear segment, and the again a parabola function. So it will, if you only draw the S curve, so it will look like something like this. So here you have a distance S and value 1, and this is time t, and this is time axis, and so your distance will initially, the distance will slowly increase, and then it will become like this. So this will be your S profile, which is the plot of distance with respect to time. Okay, so this thing is, if it's clear, this thing is easy to implement. Trapezoidal motion profile, it's easier because just you need 3 steps: constant acceleration, constant velocity, and then negative constant acceleration. But there is a problem. The problem with these kind of thing is that the motion is discontinuous, and it also may cause sudden change in accelerations, you can say, or you can say some jerks also, because here you see that acceleration here was 0 and suddenly the acceleration is constant. So if you plot your acceleration curve, it will look like something like, initially the acceleration was 0 and then suddenly it became constant, and then again it became 0. Okay, so this is acceleration. So this is 0 and this is A. So you see that from it, the acceleration quickly changes, okay, from 0 to maximum value, and this causes jerks sometimes, and this is also not really a smooth motion. So to avoid this problem, someone came up with the second method of time scaling, which is called S-curve time scaling. So in S-curve time scaling, it tries to solve the problems with the trapezoidal motion profile. So let's see how it works. Trapezoidal motion causes discontinuous jumps in acceleration. As I showed you here, the acceleration from 0 to constant, from 0 to suddenly jumps at a maximum value. So this we refer to as discontinuous jump. Okay, so there is no value between 0 to maximum. There is only 2 values. So this causes problems. A solution is a smoother S-curve time scaling, a popular motion profile in motor control because it avoids vibrations or oscillations induced by step changes in acceleration. So yeah, so we I think it will be this method solves the problem with the trapezoidal motion profile and offers a smooth motion, and it consists of 7 stages. Okay, let's see what these stages are. So let me show you quickly the velocity profile of the S-curve time scaling, and here you see that the velocity is quite smooth change initially, and then also here also quite smooth. There are no corners like we have here, corners here, also edges, corners. So this is quite smooth changes, and it has 7 stages, 7 steps to achieve this kind of motion. So the first one is constant jerk until desired acceleration is achieved. So jerk is the derivative of acceleration, or you can call it a rate of change of acceleration. So in the first step we give constant jerk. Okay, so constant jerk means the acceleration will gradually change. Acceleration will not jump from 0 to maximum instantaneously. Instead, the when the jerk is constant, then and your acceleration gradually increases, okay, and so your velocity. So notice that in this case, when the acceleration gradually increases and the velocity also slowly increases, so this avoids the problem of discontinuous motion and the shakiness in the robotic arm. After this step, we have a second step, and this step is similar to what we have in the trapezoidal motion profile, and it contains constant acceleration until the desired velocity is being approached. So from here, in the second step, we have a constant acceleration and your velocity will gradually increases. In the third step, we have constant negative jerk. So here the jerk was positive, this was positive jerk, and here in the third step we have a negative jerk until acceleration equals to 0. So here our jerk is negative from this stage to this stage, and when the jerk is negative, then your velocity will actually slowly the rate, your acceleration will be negative, and you see that the rate of change of velocity is becoming slower and slower until it reaches a maximum value. In the fourth step, we have the constant velocity phase. So in this phase you have the acceleration is equal to 0 and the velocity will remain constant, as we have seen in the trapezoidal motion profile. In the fifth phase we have constant negative jerk. So from here we have to give a negative jerk, and so this will decrease the velocity, okay, but gradually. And similarly in the sixth phase we have constant deceleration phase, and here we have the change of velocity will be gradual, okay, and while the acceleration remains constant, but the acceleration is also negative. And finally we have here the constant positive jerk until the acceleration and the velocity reaches 0. So from here we have to give a positive jerk here, and so that your velocity and acceleration finally reaches 0 and the robot stops there. So using these 7 steps, the advantage of this kind of motion profile is that the edges are now rounded off. So there is no really discontinuous motions, or there are no jumps in the motion. Everything starts gradually, slowly, and smoothly, and it also stops there, and then again when it wants to even when the destination is going to reach, then also it repeats the same pattern as we have done earlier. So these kinds of motion profiles, they are quite common in the motion planning. And so, but if you compare both, trapezoidal is easier to implement, but S-curve is more, I would say, more smoother and more practical. So the section for the motion planning and path planning, it is finished. If you want more details about further path planning algorithms, you can consult the book, and there you will see the further different methods for path planning and motion planning. But
we shall stop here and we shall now start the section for robot programming. So a number of different techniques are used to program robots. Principal task of robot programming is to control the motions and actions of the manipulator. So why we do programming of the robots? Because we want to control the behavior, the motion of the actuator, its gripper, its joints, and the task it is going to do. So for that we need commands, we need programming. A robot is programmed by entering the programming commands into its controller memory. So how a robot, usually an industrial manipulator, it has some kind of controller attached to it, and there you can enter your programming commands or code, and then this controller will command the joints to move and also the gripper to open or close. So basically there are two methods for robot programming. The main one, the first one is the online programming method, and the second one is offline, and we shall see what's the difference between them. So online programming takes place at the site of production itself and involves the work cell. So where your robot is actually mounted in the production or in the factory. So if you want to program your industrial manipulator using online programming, so what you have to do, you have to actually go to its work cell, okay, and then you have to program your robot. For example, here in this figure you can see that this is the work cell of your robot, and the person, the programmer, actually entered this work cell, and there now it will program this robot. So this is online programming. It involves stopping the robot, taking it out of production and putting it into programming or teaching mode. So the first thing you need to stop it. Robot, previously if it's doing some job, let's say painting or pick and place or welding, you need to stop it, and then you have to actually take out of the production. Not actually, for example, let's say if it's in the welding environment or in the painting environment, so you have to remove your robot from this environment a little bit, and then you have to turn on the programming or the teaching mode on the robot. Programs are then created or modified using the articulated robot. The main programming methods in the online category are teach pendant and lead through programming. So these online methods, they are further categorized into two categories. So teach pendant based programming and lead through programming. So we shall see what's the difference between them. Online programming is convenient and easy method for programming when tasks are simple and revisions or adjustments can be made on the spot. However, the production line must be stopped during the programming, and there are safety issues to consider, as the programmer must work within the robot's work envelope. So these are some concerns about the online programming method, as the programmer must enter the work cell, it must work closely with the robot, so there are safety risks there. So yeah, so this was online programming, and let's see one of the two methods for online programming, and this is the first one is the teach pendant based programming. So if you have ever been in a robotic industry where there is a lot of automation, there are some robotic manipulators, industrial manipulators. So you must be familiarized with these teach pendant, this equipment that is used to program the robot. So this is called teach pendant. So it's like a controller for the robot, or where you can enter your commands and then you can move the robot. Now also simultaneously you can program the robot. It is a most common method for programming industrial robots. Which method? Teach pendant based method. It is estimated about 90% of industrial robots are programmed through teach pendants. All industrial robots come with compatible pendant, which is handheld device that plugs into the robot. So what you have to do, you have to take this device into your hand, okay, and then you have to plug it into the robot. As you can see here, this guy is sitting, he's holding this teach pendant here, this device, and now it is teaching or programming this robot to perform some actions using teach pendant. Programmers can then use the pendant's interface to create or modify application programs. So as you can see, there are a lot of buttons there. If you see in this figure, this is also, so you see there are a lot of buttons with specific functions. You have a liquid crystal display, and then you have speed bars that shows the speed of the robot, and then data entry button, programmable function buttons you have here, and emergency stop switch, this bigger one. This is very important because the programmer is working in a very closed environment, close to the robot. So this is very important. In case if things goes wrong, if your program is not correct, or you accidentally press some high speed motion button, then you can stop it from here. So you see that everything is almost a single color, every button, but this color is marked with a prominent color, red color, with a prominent background also. So safety first. It uses a teach pendant to direct the robot's movement, which allows trained personnel to physically lead the robot through the desired sequence of events by activating the appropriate pendant button or switch. Position data and functional information are taught to the robot, and a new program is written. Taught data is stored in pendant's memory, then transferred to the robot controller. So what you do here, you move your robot. Okay, for example, let's say if you want to pick this you want to pick this object, and you want to place it in this box. So this is a pick and place operation. So what you need to do is to first move your robot here on top of this object using this teach pendant, and then you have to store this location. This will be your first location, and then you have to move down and store the coordinates of the gripper. Okay, and then you have to close your gripper, and then meanwhile you're storing all this information in your teach pendant memory, and then you have to move your robot from here and then to this location, and then finally open the gripper. So all these sequences, they require a careful planning. Okay, and also you have to meanwhile you are storing this information, every action that you are doing, so it can be later, it can be repeated. So but initially this data is stored in the pendant's memory, and then once you are sure that it's working, then you can transfer it to the robot controller for further automation. When using this technique of teaching or programming, The person performing the teach function can be within the robot's working envelope with operational safeguarding devices deactivated or inoperative. So of course there are some other devices for safety. Let's say there are some proximity sensors that detect that there should be no person inside this work envelope, otherwise the robot will not move. Okay, so you need to first disable those safety measures that are by default are there. So you can sit there, you can program, and then you can manually program your robot. So let us see what are the advantages and some disadvantages of using the teach pendant based programming. So the advantages are no extra hardware or software is required. Only you need teach pendant which comes with the robot. You don't need to buy some extra computer, okay, for programming. Most technicians are familiar with teach pendants because it comes with the robot, industrial manipulator. So during the initial training, most technicians, they already have introduction about this teach pendant, and it's also not really hard to understand. It's just simple buttons. Okay, there is no like, you don't have to learn a programming language or some code, just simple buttons, and you just need to move the robot while storing the information, and yeah, that's how it works. Best for simpler application. This is also important because for complex applications it will be too much moving the robot for each and every stuff. It will be not a feasible option. And the disadvantage of teach pendant based programming are slow movement of the robot while programming. Of course you need to move it slowly because otherwise there is a chance that you will lose precision and accuracy, and also you can hurt something, you can damage something. Suspension of production while programming. So of course when you are programming your robot using teach pendant method, you have to first remove the robot from the production, and then you have to teach it. So that's a problem. Meanwhile, when you're programming your robot, your production is stopped actually. So this is a disadvantage. The third disadvantage is it requires robot to be taken out of production, increasing downtime. So again, it's time consuming, okay, because the production is stopped, and you may have to also physically remove the robot from the actual location, because the location might be dirty. It might be like if there's painting or something, the person cannot actually sit there. Okay, so you have to physically take the robot out to a normal clean room, and there you have to program it. So this also consumes a lot of time, like shifting the robot, removing the installing, reinstalling. So, and finally the fourth disadvantage is pendants require knowledge of brand specific programming language. So this also, the pendants, they are not same for every robot. There are not, I guess, universal pendants. So for different companies like KUKA or ABB, they have their own pendants, and of course their buttons will also look different, and also their programming method. Okay, so you may call it as a disadvantage, because once you're familiar with, let's say, teach pendant of a KUKA robot, and then you shift it toward the ABB or some other company robot, then it will be, you need to again adjust yourself, you train yourself to learn the new method of programming. Okay, so this was the first programming method, online programming, and we studied online programming and especially the teach pendant based programming. So let's move toward our second method of online programming, and this is the lead-through programming. This is also online programming. Okay, lead-through programming. Lead-through programming requires the operator to move the robot arm through the desired motion path during a teach procedure, thereby entering the program into the controller memory for subsequent playback. So in this programming method, you actually don't need a teach pendant. Okay, this is even more simpler. This is online method. The first thing is online method means you have to physically present in the work cell of the robot or near the robot. You have to interact with the robot, and you have to remove the robot from the production and then start programming. So this method actually don't require a teach pendant. Lead through is a convenient for programming playback robots with continuous path control, in which the continuous path is an irregular motion pattern, such as in spray painting. So if your path is continuous, for example, in the previous example, we saw that in the pick and place example, you move to a point to pick an object, you open your gripper, close your gripper, and then move to the goal position. So those things are easier to teach with your teach pendant. Okay, but if you want continuous path, okay, then this lead through programming method is more suitable. Why it's suitable? Because in lead through programming, you actually physically move your robot, or it's some kind of its model, a smaller version of its the same robot. You physically with your hands you move this robot, okay, and then there are some buttons where you have to teach your robot, okay, here you have to stop, here you have to close your gripper, but there is no teach pendant actually. So you're applying the force needed with your hand, and if the robot is big, then you need actually a smaller version of your model robot, and there you teach your robot. This programming method requires the operator to physically grasp the end of the arm. So this is important, physically grasping. But in the teach pendant based programming, there was no physical grasping. You only hold the teach pendant, and actually you don't need to physically apply the force. But here you actually have to grasp the end of the arm or tools attached to the arm and manually move through the motion sequence, recording the path into memory. So this is a difference here. So that's why this teach pendant based programming, it's also sometimes called powered lead through programming. Okay, so because the robot arm itself may have significant mass and would therefore be difficult to move, a special programming device often replaces the actual robot for the teach procedure. So yeah, this special programming device, you can also, if your robot is big and you cannot actually move with your hand, so you can use a smaller version of, or some kind of similar kind of smaller device that you can move with your hand easily to teach your robot. The programming device has a similar joint configuration to the robot, and it is equipped with a trigger handle or other control switch, which is activated when the operator wishes to record motions into memory. The motions are recorded as a series of closely spaced points. During playback, the path is recreated by controlling the actual robot arm through the same sequence of points. So if your robot is big, you just need a smaller version of the same robot with same configuration. Let's say if you're using this articulated robotic arm with 6 degrees of freedom, but it's big, then you need a smaller version and you just move this smaller version with your hands, and there is also some buttons to tell the robot that here you have to stop, here you have to activate your gripper, and then you have to save the program, the sequence of the program, into the controller. So what are the advantage? The advantage of lead through programming is that it's easy to program and does not require deeper programming experience. It's even easier than the teach pendant based programming, because you don't need to actually learn how to operate information about the buttons on the teach pendant. So you're just like teaching a child by you remember when you teach the student or children about writing, so sometimes you hold the hand of the children and then you teach them writing. So this is similar. Of course, it has disadvantages also. The disadvantage is interruption in the production, because it's an online procedure again. So you have to stop the production during programming. No interface to other computer subsystems in the factory. So in this method, you actually, because there are no other computers there are involved actually for example, language-based programming. So you cannot really, if you have this kind of programming system, lead through programming system, if your robot can only be programmed through the lead through method, then the problem is that you cannot really connect it with the other computers or other systems where you can just program on the computer and download the code there. And the last one disadvantage is it lacks precision, because you're moving the robot with your own hand. Okay, so sometimes the person hand is shaky or it's not accurate. So when the robot actually playback your motion sequence, then it will definitely not as accurate as if you do it using teach pendant or using manual programming. So this was a second method for robot programming, which was a sub method for online robot programming. Now let's see what is offline robot programming method. So what was in online programming? That you have to physically present in a robot work cell, and there you have to interact with the robot and physically teach them about your motion sequence or program them. But in offline programming, things are quite different. In offline programming, it is accomplished on computers located away from the robot station. Using simulation software, data is generated and then sent to the robot controller, where it is translated into instructions. So here you see that this is again this is your industrial manipulator. And it has a gripper here and has some 3 joints, and this is connected to these are the controllers, and so this whole area is a production area. Okay, this is, you can call it the work cell. And so this production area, this controller, so they are connected to the robot, and also they are connected to the offline programming computer, where a programmer can just sit and it can write some code, programming code in any language, and then it can first simulate this program. So there is also in your there are softwares available where you have simulated robots available, where you can actually simulate how your code is going to work. And once this simulation is perfect, then you upload this code into your controller, and then your controller will actually execute these commands. Additionally, the software contains modeling data which assists selection of the best robot configuration for a particular application. So of course here now the computers are very powerful, so you can actually model and simulate almost any kind of robotic arm in a software before actually executing the commands in the hardware phase. The advantages of offline programming is that it is safe for programmers, again because the programmers are not physically in contact with your robotic arm, so there is less chance that they will get hurt by some kind of accidents, or if the program isn't working properly, then there is a less risk for accidents with the robot. The second advantage is verification of program through simulation and visualization. So this is again the best thing in offline programming, is that you can actually model, simulate your robot, and check the validity of your check the correctness of your written code. Okay, so whatever you have code you have written, you can actually verify it before actually physically running it on the robot. You can in a simulation software you can see how it works, and this will actually helps to avoid some accidents or some problems in the future. Production can continue while programming. So this is again a very plus point, an advantage. Your robot is working like previously normally, and you're making a new modified program or an updated program, and you can here testing it in a simulation while your robot is working already. So you're saving actually a lot of time. The time otherwise you are spending on the robot, shifting it, installing it, reinstalling it, and yes, so this is a great advantage. So now let's see what are the disadvantages. Demands investment in offline programming system. So if your robot is not previously offline programmable, it's only online programmable, so then you need an updated controller that can actually interact with some offline computer outside the work cell. Okay, so you need additional or an updated controller. And the second disadvantage is it needs extensive training. Training of whom? Training of programmers or technicians, you can say. Because why it needs training? Because your technician may have to learn a programming language. He may have to learn a new programming language, and of course learning a new language, it requires time and also effort, so and also a lot of training. So because it's not only about programming, it's about using the software for modeling your robot and also software for actually simulating your robot. So all these things, they require investment of time, money, human resources. The third disadvantage is I would say nowadays the computers are not that expensive, but still the disadvantage is because this method, it uses a computer. Computer might not be that expensive, you can buy it for a cheaper price, but the simulation software for industrial level accuracy, these professional software for robot simulation, they may be very expensive. Okay, and again the communication, also the specific communication systems, they also require some additional licenses, and they might also contribute to increase in your price. So yeah, so these are some advantages and disadvantages of offline programming. If I have the opportunity, I will go for offline programming instead of online programming, and the big reason is the safety. Okay, now let's quickly move to the overview of some robot programming languages. Virtually, robots are programmed with some kind of robot programming languages. These programming languages are used to command the robot to move to a certain location, signal outputs, and read inputs. The programming language is what gives a robot its flexibility and allows a robot to react to its environment through the use of sensors and to make decisions. So again, we are talking about now the offline programming, and in offline programming we have to use some programming languages, and for the programming languages, what's going on here, you write some code, some algorithm, and you're taking some input, make some decisions, and giving some commands. So that's all about the code that you have written in any program. So there is an algorithm with some commands, and you're making some decisions, giving some commands, getting information. So that's what's going on. Robot programming languages fall into three basic categories. So the first one is specialized robot languages. These languages have been developed specifically for robots. The commands found in these languages are mostly motion commands with minimal logic statements available. Most of the early robot languages were in this type, although many still exist today. VAL is an example of this. So they are specifically designed for your industrial manipulators, these languages, and mostly the commands are about motions, like move forward, move up, move along x-axis, open the gripper, close the gripper, and yeah. So the main feature of these languages is that they are specialized robot languages. They are only for, or mostly used for, robot operations. The second type of robot language is robot library for new general purpose language. These languages were created by first creating a new general purpose programming language and then adding robot specific commands to it. So they are more like general purpose programming language, and it has also some robot specific commands. These languages are generally more capable than a specialized language because they tend to have better logic testing capabilities. So Karel language is an example of this type. So they are more like general purpose languages. And the third one is robot library for existing computer language. These languages are developed by creating extensions to popular computer programming languages. Consequently, these languages closely resemble traditional computer programming languages and benefit from the power of existing widely used languages. Robot script is an example of this type of language. So for example, if you have a general purpose language and you need you can use this general purpose languages with some additional library which is specific to the robot, and you can actually program your robot with this general purpose language. And yeah, so these are the three different categories of the languages, and let's see one by one a brief introduction about further languages, actually which languages are being used in robot programming. So again, we are talking about here the offline programming of the robots. So the first one is Wave. This is again a programming language. Wave was the first high-level language created for programming a robot. Stanford Artificial Laboratory developed it in 1973. So this just gives you some introduction about different programming languages. And then you have the ARM language. This is again a high-level programming language, and it was developed by the Robotics Research Center at Stanford University. Then you have the MML. MML was model-based mobile robot language that was developed at the University of California. It is a high-level offline programming language which contains functions for high-level sensor functions, geometric model, description and path planning, and others. This language contains an important concept of slow and fast functions, which architecture is essential for real-time control of robots. A slow function is executed sequentially, while a fast function is executed immediately. The second important concept is the separation of the reference and current posture, which makes precise and smooth motion control and dynamic posture correction possible. Okay, another type of the robot programming language is the robot independent programming language. It is based on an object-oriented robot independent programming environment. The RIPE computing architecture consists of hierarchical multiprocessor approach, which employs distributed general and special purpose processors. This architecture enables the control of diverse complex subsystems in real time while I think it's a mistake. Okay. This architecture enables the control of diverse complex subsystems in real time while coordinating reliable communication between them. So VAL, I think we already have this example before. So this was a robot specific language. This is a type of robot specific language. VAL stands for Victor's Assembly Language. VAL is a high-level programming language developed for Puma lines of robot. The programming language is similar to BASIC. It is a complete set of vocabulary words for writing and editing robot programs. So it is a high-level programming language. Okay, and this is also a robot-specific programming language. One thing I mentioned here that may not be actually, I mentioned that these languages are for offline programming, but it might not be actually true for all of them. because even for online programming, when you are writing code, okay, with your using your teach pendant, so it might be also being converted into some kind of language. It may be some basic kind of commands, simple, or it may be some kind of very basic language like assembly language. So yeah, so then we have two more languages that we need to see, and we must have introduction about them. And then we have the instruction based learning language. It is a method to train robots using natural language instructions. IBL uses unconstrained language with a learning robot system. A robot is equipped with a set of primitive sensory motor procedures such as turn left or follow the road that can be regarded as an execution level command language. The user's verbal instructions are converted into a new procedure, and that the procedure becomes as a part of knowledge that the robot can use to learn increasingly complex procedures. With this procedure, the robot should be capable of executing increasingly complex tasks. Because errors are always possible in human-machine communications, IBL verifies whether the learned subtask is executable. If it is not, then the user is asked for more information. And then finally we have ladder logic. This we are going to study in detail further in our next lectures. And ladder logic is a programming language designed to be used by electricians. It closely resembles the relay logic that appears on the inside lids or doors of dishwashers and washing machines. The only robots that use ladder logic programming are those that come with a controller or with a programmable logic controller. So the ladder logic we shall see in the detail in the upcoming lectures, and for now we only have an example of VAL based programming. So let us see an example of robot programming using VAL language. The VAL language is the most advanced commercial language designed for use with Unimation Incorporation industrial robots. So Unimation is the name of the company, and so they were making the industrial robots. And to program those robots, they were using this VAL language, and this language stands for Victor's Assembly Language, and some texts refer to it as Variable Assembly Language also, but most of the references they point it out as Victor's Assembly Language. So it is basically an offline language in which the program defining the motion sequence can be developed offline. In the previous slide we have studied that this is a robot specific language. It's not a general purpose language, and also it is a offline programming language. To demonstrate the VAL language, let us assume that the robot must pick up objects from a chute and place them in successive boxes. One possible sequence of robot activity is as follows. So the robot has to pick some objects from the chute and then place them in the boxes. So what will be the sequence of the activity? So the first, it could be that the robot will move to the location above the part in the chute, and then move to the part. After that, close the gripper jaws, remove the part from the chute, carry the part to the location above the box, put the part in the box, open the gripper jaws, withdraw from the box. So these are the sequence of activity that the robot must perform to execute this task. Now let's see how the corresponding VAL program looks like. So this is edit demo 1, and then you have to write program demo 1, and then you have to write this command with 50. If you want to see what's going on here with each command, we can also see the meaning of each line in this. So the first command that says appro part 50 at the rate of, so it means that move to the location 50 millimeter above the part in the chute. Okay, and then moves part at the rate of, move along the straight line to the part. Okay, and then close, this must be close the gripper jaws as here stated, and then you have the departs 150, withdraw the part 150 millimeter from the chute along the straight line path. Approach box 200 at the rate of, move along a straight line to a location 200 millimeter above the box, and then move box. So put the part in the, so if you want to just put the part in the box, you have to just write this command move box, and then your part will be in the box. Open I, so this will open the gripper jaws, and then depart, and then your robot will be withdraw from 75 millimeter from the box. So this is, I guess this is default withdrawal distance. So this is an example of Victor's assembly language. It's really not difficult, just basic commands: open, depart, close, move. So it's not really difficult to program. When the program is executed, it causes the robot to perform the steps which describes the task. For a given robot, the only parameters necessary to locate the end effector, gripper, welding torch, etc. of the robot completely are the angles of each of the joints. However, there are many different ways to define the points for the robot to move to, some of which can be much more efficient depending on the task to be accomplished. Okay, so this was a small example of the robot offline programming, and we will mostly stick to the ladder logic, in which you will see in the upcoming lectures. And with this, we end our lecture here. Thank you very much for listening, and if you have any questions, feel free to contact me by email. And yeah.